Hey, welcome back to EC 382. Dr. Bax here. This is Module 12, and we are going to study how to control motors with pulse width modulation, or PWM. So the basic goal is we are to move the robot at various velocities. Okay, so what it means is basically move forward, backwards, and rotate the robot. So we should be able to control each motor independently at different speeds. So can move slow or fast, or just move backward and slow and fast. And sometimes we need to rotate the robot like this. And then sometimes we should be able to rotate the robot about itself, right? So to control the motor speed, there are a few different methods. So the first one I want to show is we're going to connect a variable resistor with a motor in series. So this variable resistor is also called potentiometer. So let me call this potentiometer Rx, right? And then the Rx can be 0 to 100 ohms, right? So we can change the resistance of this potentiometer, right, to to control the speed of the motor, right? And if we apply higher voltage across the motor, then basically we're going to have higher speed, right? So for example, if we set Rx equals 1 ohm, okay, and then let's use a voltage divider from, I believe, from ECE 315 or ECE 215, right? So then VM, the voltage across the motor, equals Rm over Rx plus Rm times Vs. The Vs is the voltage supplied to this circuit, right? And then that is going to be what? Rm equals 10 ohms, and Rx is 1 ohms. Rm is 10 ohms times 5 volts, right? So that is 10 over 11 times 5. That's going to be about 4.5 volts. Okay, and then that gives us high speed, right? And then if we set Rx equals, for example, 90 ohms, okay, much like 90 times higher than this 1 ohm, right? And then let's see what happens. So Vm equals same as before, right? And then it's going to be 10 ohms over the Rx is now 90 ohms. And then Rm equals still 10 ohms and times 5 volts, okay, which gives us 0.5 volts, okay? So compared with this 4.5 volts, which was high speed, this 0.5 volt will give us low speed. Make sense? Yep. So if the potentiometer's resistance is only 1 ohm, very small, then we will have higher voltage across the motor, and then that gives us a high speed. If we set a high resistance for this potentiometer, then it will give us low speed. Okay, very simple, but there is a huge problem on this design. So let's look at power consumption. Okay, so you're gonna use the same setup, right? And then Rx equals 90 ohms, right? And then we had the 0.5 volts across the motor. Okay, let's look at the power. So power equals Vm squared over Rm. So Vm is 0.5 volts squared over Rm is 10 ohms. Okay, which gives us 0.025 watts, which is 25 milliwatts. And then how about the power consumed by this potentiometer? So then we need to find out the voltage across this potentiometer, which we can find Vs minus Vm. So Vs equals 5 volts, and Vm is 0.5 volts, which is 4.5 volts, right? And then the power consumed by the potentiometer is going to be Vx squared over Rx, or 4.5 volts squared over Rx is 90 ohms. Okay, so if you calculate that, we have 0.225 watts, which is 225 milliwatts. Wow, so this is almost 10 times greater than this voltage. Sorry, the power, right? And then let's look at the power efficiency on this case. So if you remember, still from 215 or EC 215 or EC 315, so power efficiency is a useful power over useful power plus wasted power, right? So useful power is the power delivered to this motor, right? And then power wasted is the power dissipated on this resistor, right? So Px. So Pm is 25 milliwatts, right? And then Px is a 225 milliwatts. And then I have 0.1, okay, which is about 10%. So power efficiency is only 10%, which means a lot of power, or in this case, 90% of total power is wasted, right? So this is a bad design, right? So we never use, this design to control a motor. So because, instead of delivering a lot of power, more power to the motor, we basically waste a lot of power at the resistor. Okay, so let's look at the second method. Okay, so basically we want to use pulse width modulation, or PWM. Okay, so basically we have a on off switch, right? So when the PWM equals on, okay, or 3.3 volts, okay, so in this case 3.3 volts, okay, and then let me just change this back. Let me just talk to the off case first. So if the PWM is off, right, and then that is going to be 0 volts, right? That means then 0 volt across the motor, that means simply just no current flowing through, right? So there will be no power, right? Yep, that makes sense. When the PWM is on, which means we have a 3.3 volts, like here, okay? Then there is no resistance here, right? So all the power is delivered to this motor, right? So all the power is consumed at the motor, right? Which is basically 100% efficiency. Wow, this is good, right? This is really good. Okay, but let's look at how much current should P1.2, this port, provide. Okay, so we have Ohm's law. Okay, so Im equals Vm over Rm. So Vm is so voltage across the motor, that is basically 3.3 volts, right? And then the resistance on the motor is only 10 ohms. So that means we have 300, 330 milliamperes. Okay, So 330 milliamperes, this is a lot of current, right? So the MSP432 GPIO pins can only provide a current up to about 10 milliamperes, okay? So if you really hook up the motor to a port like this, then basically, you will fry the board. Okay, so never try this way because the motor is trying to draw about 330 milliamperes, and then the MSP 432 try to deliver that much of a current, then what it only can do is just fry itself, right? So this is not a good design. Well, then what can I do then? Right? So let's look at this third method then. So basically we want to have external switch. Okay, it is a switch, but it is basically a electrical switch, or this is called MOSFET. Right? So this part here, this is a switch. This is a MOSFET. Right? This is basically the same as switch like this. Okay, and then just you close, then it is on, so the current can flow through. Okay, if you open, then current cannot flow through, right? So MOSFET is simply a switch. Okay, and then we're gonna supply 5 volt to the motor from battery. Okay, so our battery on your robot can provide about 7.2 volt, but let's just have 5 volts here in this example, right? And then if we provide a pulse width modulation from MSP 432, okay, then when PWM equals off, same as before, there is no power, right? So because basically there is no current flowing through here, okay, because the switch is open, right? And there is no current, and then no power can be delivered, right? And then when the PWM equals on, okay, and then we have almost 100% efficiency. Okay, so in that case, here the motor is about the RM equals about 10 ohms. Then current flowing through is IM equals about 500 milliamperes. Okay, when the PWM is on, right? And then PWM duty cycle is can be 0% to 100%, right? So and then this one, using this PWM duty cycle, we can have speed control, right? Okay, so because the power is conserved, right? So that means input power should be the same as output power, right? In this case, the input power to this system is electrical power, and then the output power is the motor, right? So the output power is mechanical power. Okay, so electrical power is Vs times Im. Okay, the voltage times the current, and also we need to multiply by the duty cycle, or duty cycle is high, right? Divide by DC high plus DC low, right? This is so when the duty cycle is high, then we can provide the power to the motor. When duty cycle is off, then there is no power, right? And this one should be the same as tau times omega, where tau and omega is basically torque times angular speed. Okay, And then this DC means a duty cycle, right? Okay, so using this MOSFET, so the power efficiency is really good. Okay, it's almost get about 100%, but there is a small resistance across this this MOSFET, so it's not really going to be 100%, but it's close to 100%, right? And then so the oops, and then so the port 1.2 can provide only PWM, right? The current flowing through here is let me call this IC or IG. The gate current is usually less than 1 milliamperes. It's very, very small, some microampere range, right? So the MSP 432 does not have to provide too much of current as the example I showed here, right? So in this case, we need to have a 330 milliamperes. But in this case, the the MSP 432 does not have to provide that much of a current, or the current flowing through the motor is from your battery, okay? And the battery can easily provide this much of current, 500 milliamperes. Is very easy for the batteries, right? Right. So, and then by changing the duty cycle, then we can control the speed, right? Right. So, but how about directions? Can you also change the directions? Okay. So we can use H bridge for direction control. So we can move forward and backward, right? Okay, so it is called H bridge because we have now 4 switches. Okay, the setup looks like this H shape, so we call this H bridge, right? So the way it works is, as I mentioned before, these are all switches, right? So let's turn this one on, right? And then this one is off, and this is off, and this is on. Okay, and let's see what happens. So because this switch is off, the current cannot go through, right? And then here also the current cannot go through here. But this one is on, right? The higher voltage from this battery, the current can go through this path, okay? And also this switch is on, then current can go through this way, right? So that means that the current can go through from left to right, like this direction, okay? And then that way, the motor runs the forward direction, right? But now, let's turn off this one, this switch, and turn on this one, off here, and on here. Then let's see what happens. Then current can flow through this direction, right? And then also can move through this direction, right? So now the current can go in this direction. So now this current, okay, is the opposite, the direction of the current is opposite of this one, right? So that means the motor runs backward direction, okay? So using this 4 MOSFET configuration, then we can move the motor forward or backward, okay? Well, we can also do something more, okay? Means which means cost and break, okay? And then let's see what happens. So let's say we can have this one off, this one is off, this one off, and this one off. Or it's okay, it's this one is on, okay? Anyway, so what happens here is the current flowing through equals 0. There's no current flowing through because, this one is off, this one is off, right? And this one is off. So there is no way the current can coming from this the battery and flow through the motor, right? So equivalently, we have an open circuit. Okay, so basically what it does, the motor is coasting, right? Or continue to spin by the inertia. Okay, inertia of the motor, and gradually it slows down. Okay, and another configuration we can have is we put off, and then on and on, right? And then suppose the current or motor was moving forward direction, that means the current was, or moving backward direction, then current is flowing through this direction, right? And then we turn this switch on, that means we just have a closed loop here, right? Or it's the same as equivalently, this is the same as this setup, right? So in that case, we have braking. Okay, so basically, it resists spinning motor. So it should stop there, right? Okay, so then, so with this H bridge, then you can control forward, backward, right? And then coast and brake. No, this, sorry, brake, right? Right, then, but can you still control the speed and then forward and backward and coast and brake? Okay, let's see this this setup then, right? So we have on, off, on, right? In this case, this is forward, right? And then, but suppose we apply a PWM signal on this MOSFET, like this, right? So it means we have on or off, right? So this one is still on, this one is off, this is off, and this is on. But I mean, on, off, on, off, on, off, right? When this is on, okay, so this is basically same as this setup here, forward direction, right? On, off, on, okay? And when this one is off, this one is the same as this setup, right? Which is coast. So that means this is forward, and this is just coast, right? And then so this is and then so the speed can be controlled by this duty cycle, right? The width of this pulse. If this pulse is longer, and then that's at the same time this one is shorter, then we have higher speed, right? Okay, and then how about this case? So this one is a backward, right? So backward, it's I showed you here, right? This is a backward direction, but if we just apply PWM signal here, right? So we have on off on this MOSFET, then when the PWM is high, that gives us a backward direction. And this is low, then we have coast, right? So this is how we control the motor speed, and at the same time, we can control the direction, forward or backward, right? Okay, so this is the theory behind the H bridge and the controlling the motors. Okay. In our TI robot, then we already have this TI DRV 8838. This is H bridge motor driver. Okay, so we have two of these, one for right motor and another one for the left motor. Okay, and then from our launch pad, so we have three signals from launch pad to a H-bridge motor driver, and then another three wires to the this H-bridge motor driver. Right. So so P27 is this is PWM, right, for the left wheel, and then this one is a direction. Okay, so forward, forward, backward, right, and then another one is a sleep. Okay, so we can put the motor in the sleep mode, and then 2.6 is also PWM for the right wheel, and then direction. So this is a forward or backward, and then sleep. Okay, so from the software side on Launchpad, so basically we need to control these three and these three, these are six ports to move the motors independently move forward or backward, and then also different speed. Okay. Right. So this is a block diagram, right? So this is Texas instrument DRV 8838, the H-bridge motor drive. And then there is another one. And then motor is connected here. Okay. And this 7.2 volt, this is a battery from the robot. Okay. So we have a 6 batteries that gives us up to 7.2 volts. Okay. Right. Then so this is the truth table or logic table for the 8838, right? Okay, so the the PWM is connected to this port. So PWM, let's say left, which is P2.7, is connected to enable port, right? So let's say this one, 2.7, and enable, so PWML. And pH is connected to DI direction, DIRL, which is P5.4. Okay, so this one. And then here, and sleep, LSP-L left, which is a 3.7, is connected to N sleep pin of the motor drive.